I'm standing here. Why don't you introduce yourself?
Yes, my name is Jorge Amaya. I am about to finish my graduation requirements from the Environmental Science program at USF, and I'm working here with TH in order to get an internship started in sustainable energy.
And what are you working on right now?
This is a very simple solar energy system. We are testing this panel that we just connected, and we are charging 4 batteries to see how the system works. And so far, it seems that the batteries are charging.
Yeah, it was 12.25 when we hooked it up. Now it's at 12.27. Let me give you the camera to you for a second. So, hello and welcome to the Rosebud Continuum Eco Science Center, and I'm Dr. T.H. Culhane from the Patel College of Global Sustainability, and Jorge is a student in the Geosciences program in environmental science. And this is a system that was recently donated to our student Nathan Lafata, and it consisted of 4 deep cycle marine batteries. These are lead acid, old technology. They were down at about 12.1 when they were delivered, so they were about 25-26%, and it said low battery. So we wired them up in parallel, connecting all of the negative terminals together. So that's the positive terminals, these are the negative terminals. And then we put this charge controller, which is a 60 amp charge controller, and plugged in the positive side of the battery to where the terminal said positive battery in here, and the negative side of the battery to the terminal that said negative battery here and here. That's the first thing you do. With a charge controller, you never connect the solar panel to the charge controller. If it doesn't have battery constancy, then it will fry. So please know that if you're attempting this at home, do not connect your solar panel to your charge controller and then to the batteries. Always connect the batteries to the charge controller first, then connect the charge controller to the solar panel. Now, when we were looking at this, when we first hooked it up, we monitored the battery. As I said, they were down at about 12.1, 12.2. We then hooked this to the charge controller. The status light started blinking saying, yeah, I'm hooked up. Then we took the positive and the negative from the panel over here, and we just used these screw terminals to bundle the negative and bundle the positive to a longer cable so that we could run it in to where the terminal here says PV positive, that's this white one here, and PV negative, that's this black one here. And I know the conventions are a bit messed up, but we're working with DC current, so we're using the black for the negative, and that's what we have hooked up over here to the black part of the solar panel. This is just the ground, which we leave hanging, and then we use the white one connected to the red for the positive. I know that in AC terminology, sometimes you talk about the white being the neutral and then the ground, and it just gets more complex. But in DC, it's just positive and negative. That's all you got. So you better stick with the convention. We like to stick with the convention that the black is the negative, and then we'll use any other color for the positive. I chose white for the positive here. So that's positive and negative coming into the charge controller and going out of the charge controller into the battery. This multimeter is telling us what the batteries are at. You can see now that cloud cover has come in. It's sort of wavering because I'm blocking it, and it's in a greenhouse, and it's an old panel. Look at all that discoloration. Look at all the brown there. This is not a highly functioning panel. Nonetheless, when the sun was brightest, we were getting 17 volts. Usually it should be 19 to 20, but these are putting out, was getting 17. Under cloud cover, it was putting out 15, and that's okay. 15 volts can push electrons into a 12 volt system. It'll keep pushing until they've equalized. If the batteries are up at 15 and this was pushing at 15, they'd be equalized, right? If this was pushing 19 or 17, it would try to lift the battery's voltage up to 17 or 19, but that would destroy the batteries. This is a 12 volt system, and 12 volt batteries are made so that they can be charged up to about 14 for a blow off, sort of shake the sulfur off the electrodes kind of situation, sometimes the charge controller will pulse stuff in at 15 volts, but usually it's about 14, 14.1, floating at about 13 to 13.5. So we don't want to just connect this panel directly to the batteries because it would overcharge the batteries even though it's not performing well and only putting out about 15 volts some of the time. You can't charge this to 15 volts all the time. It'll ruin your battery system. So we have a charge controller in between. That's the whole purpose of this box, just to control the charging so you don't hurt the batteries. Now if you didn't have this, what would you do? You could come and hook up the solar panels, have your multimeter on, and just watch it. And when it gets up about 13.5, gets up toward 14, you just unplug the solar panels. But then you got to sit here and watch it. Now, do you have to sit and watch? No, this here is called a battery monitor, a Bluetooth battery monitor. It takes from 6 volts to 20 volts at 1 milliamp of use, so it is using a little bit of power. It's a Bluetooth dongle from our phone app, which is called the Ansell phone app. As long as we're in Bluetooth range, we can sit comfortably in an air-conditioned space, out of the heat, and we can monitor when this battery is charged. The app on the phone tells you whether it's low battery or high battery, and then you can come running out and disconnect it. It's not like it would overcharge in an instant, so you have time to walk over and disconnect it. That's if you couldn't afford these. But charge controllers range anywhere from $20 or $30 for a small one that can be anywhere from 10 amps to handle 20 amps. This is a 60 amp. These cost, I've seen these run for about $60. So usually the amperage and the cost have somehow matched each other. I have an 80 amp over down by my RV, and that cost me several $100s. So it's not a linear phenomenon. But a charge controller is necessary. Usually a 100-watt panel will have about 5 amps that it's putting out. And how do you calculate that? Well, wattage is amperage times voltage. So if you say, oh, I got a 100-watt panel, and you measure the voltage, because it's not easy to measure amperage unless you have, well, in DC it's pretty tough. You have to have an inline way of, and a load on it to see what the amperage is. So you measure the voltage, check what they say the wattage is, and then you just divide. So 100 watts divided by roughly 20 volts is 5 amps. So this is not going to produce more than 5 amps. Since this is a 60 amp charge controller, it means I can hook 12 of these panels together. In fact, we have 13. We have 6 on the wishing well by the windmill over there that we're going to use, and we've got 7 of these old panels. We're probably going to be safe using all 13 because these are probably, with that discoloration, the age of these old 100-watt panels, they probably are not putting out 5 amps each. They might be putting out 3 amps or 4 amps. So we're going to look at it, but we think we can get all 13 in and stay within the limits, the tolerance limits of this charge controller. The battery bank is very small. It's not going to power a lot. We're going to throw an inverter on it next so we can power some loads. This is a small inverter. This is 2,000 watt continuous, 4,000 watt peak if you wanted to turn over a motor of an incinerator, food grinder, or a drill or something to kick that over. And this is going to be wired in right to the terminals, positive and negative, with separate wires. So we're probably going to have to look at taking this one here. Yeah, that's what we'll do. We will attach this here, and we will attach this back here, and then we will put them into the back of the inverter. Then we can put the inverter up on the table, maybe over there, and then we can run AC cords in. The problem is there's no way to monitor the battery level from the inverter. So if you're just running fans and blowers and pumps and you start draining the batteries, you're not going to know unless this has a shut-off alarm, and I don't see that it does, but it might. If it did, then when it gets down to about 10.5 or 11 volts, this thing will start whining like crazy, going beep, and then you've got to run off and you've got to shut it off immediately so that you don't drain the batteries too low. So there's disadvantages with a system like this where you're using separate components, but that's the price you pay for not paying a high price. If you buy a really good inverter charge controller package that's all in one unit and it has the right shutoff, it's much more sophisticated, then you can plug stuff in and leave, and then it'll automatically disconnect. These systems don't necessarily do that. So that's our next phase, is getting this inverter hooked up to here. Now you can see we're up to 12.33, so clearly the sun is charging the batteries from this one panel. So we have a success there. All right, we'll get back with you after we've hooked up the inverter.